In this video, we are going to work on section 8.2 from your textbook, which is going to be about sampling distributions again, this time talking about the distribution of the sample proportion. So we might say that Midland College students fall into one of two categories. Either the student went straight from high school to college, graduated in May and went to college starting in August, or the student may have taken a break between high school and college to get some work experience or to travel or do whatever they needed to do for some time or some years in between. So we are going to consider a situation. We're going to consider that there are about 5,000 Midland College students. And I don't know that this is true, but we'll just suppose that 2,000 of them took a break in between high school and college. So the other 3,000 would have gone directly from high school to college. Then step 3 says we're going to randomly sample 30 of them. So basically assign all 5,000 Midland College students just an index number that numbers them 1 through number 5,000. And then we are going to use a random number generator to randomly select 30 of those numbers assigned to students, and that will allow us to randomly select 30 students. In step 4, we're going to calculate the sample proportion. So our n sample size is 30. X is going to be the number of students we find that did take a break between high school and college. And so this p hat is going to be the sample proportion. And the p hat is just what proportion of our sample did take a break between high school and college. And then if we want to, really see that this statistic, this descriptive statistic, the sample proportion that we're calculating, if we want to see that that is actually distributed, we might repeat steps 3 and 4. We might take another random sample of 30 students and calculate the same sample proportion again. But you know that depending on which 30 students that you randomly pick, you're going to get a different sample proportion. You won't get the same sample proportion every single time, but it will always be just a little bit different depending on which students you choose. So if we repeat this a whole bunch of times, we'll have maybe most of our sample proportions pretty close to 2/5 because that's the population proportion. And then we might have some sample proportions that are like 0, because it is possible, in this case, to randomly choose 30 students that just happen to all go directly from high school to college. And you might have some sample proportions that are actually 1, because it would be possible to randomly sample 30 students who all took a break between high school and college. And so we're going to find everything in between 0 and 1, but this is the point of the exercise, to show that the sample proportion, p hat, is distributed in some way. In other words, it is a random variable itself, and it follows some probability distribution. So let's do this on Microsoft Excel to demonstrate what it is we're talking about here. In my example, I said that there was 5,000 students, 2,000 of which took a break, and that means 3,000 did not. And so I'm going to let 1 represent those students who took a break, and I'm going to let 0 represent a student who did not, who went directly from high school to college. Okay, so that means I should be seeing 2,000 ones and then followed by 3,000 zeros, and that would be one way to represent this population. So I have to drag these ones down to fill up 2,000 rows. Here's 1,000. Here's 2,000. So here's 2,000 ones. followed by, like I said, 3,000 zeros, so that these zeros fill up the remaining students in my 5,000 students. It takes a while to drag these down. Okay, so then I've got zeros all the way down to row number 5,000. So we've got 5,000 cells representing 5,000 students. A 1 tells me that that student took a break, and a 0 tells me that that student went directly from high school to Midland College. Now let's use my fancy program, and I'll have to move this over, I think, to see, well, let me look at something. Yeah, so what my fancy program is going to do, just like before in the previous video, is this is going to, hold on. Okay, now I think we're ready. We're going to go to this, and we're finally going to run it. And by the way, what's happened is that I've allowed the program to randomly select 30 students out of the 5,000 students, and then calculate the proportion that ended up taking a break, the proportions of ones out of those 30 selections. And so we'll just calculate the sample mean and the sample standard deviation really quick. And so the sample mean, I type in equals average of column C. And for the standard deviation, do stdev.s of, again, column C. And so this allows me to calculate basically what am I getting for the mean of these sample proportions and the standard deviation of these sample proportions. So in column C, I have the sample proportions for a sample size of 30 students. And again, these are different. My point was, depending on which 30 students you choose, you are going to calculate different sample proportions. And the majority of them fall pretty close. The majority of them fall pretty close to 2/5, which is the same as 0.4. But some of them are going to be greater and some of them are going to be less. We can visualize this by going to Insert on the ribbon and inserting a histogram. And you can see that I have some sample proportions that go all the way down to 0.1, not quite all the way down to 0, and some sample proportions that go all the way up to like 0.66, not all the way up to 1. But you can see that this pretty much follows, this histogram pretty much follows a normal distribution, or it follows a bell-shaped curve if you're looking at this histogram. And so not only are these sample proportions distributed, but they are seemingly normally distributed based on this just visual empirical evidence we have. So we'll get rid of that. Go back to my notes really quick. And this is the procedure that we just followed, 1 through 6. Now here's some theory. If we take a random sample of size n, or size 30, with population proportion p, and by the way, that p without a hat, it represents the population proportion. The p with the hat represents the sample proportion, right? So my population proportion in my previous example was 2/5, or 0.4. And we calculated a bunch of different sample proportions. Now x is going to be binomially distributed with parameters n and p. X is, remember, the number of students in the sample who did take a break between high school and college. And we can think of each student as being a Bernoulli trial. We'll just assign a success as a student that took a break and a failure as a student who didn't take a break. Again, to remind you, success and failure doesn't mean the same thing it means in everyday language. This is just statistics vocabulary that we use to talk about Bernoulli trials. But then x is the sum of the number of successes from several Bernoulli trials, so that means that x is binomially distributed. If you need a refresher on that, go back to chapter 6, which you guys did just before spring break if you're in my online course. So it's binomially distributed with parameters n and p, where n is the sample size, and p is going to be the probability of, quote, success for, any of those Bernoulli trials. But that probability should be the same as the population proportion, right? Because if you're randomly selecting an individual from a population with population proportion p, well, then the probability of selecting a individual of one type would be p, right? So it's convenient that the population proportion lowercase p and what we've been using for the Bernoulli trial probability, lowercase p, is the same symbol because it works. Now, I'm going to tell you just that p hat is also follows something that looks very much like a binomial distribution. We just scale it down in terms of the x-axis. So instead of the x-axis ranging from 0 to n, this is going to get squished together so that the x-axis ranges from 0 to 1, because a proportion has to be between 0 and 1. Otherwise, it's going to look exactly like a binomial distribution. We've also seen in previous lessons and previous chapters, like in chapter 6, we saw that the variance of the binomial distribution is n times p times 1 minus p. And if that variance is greater than 10, then the binomial distribution looks like the normal distribution. In fact, the binomial distribution looks so much like the normal distribution that the normal distribution approximates it well. So this is true, this n times p times 1 minus p greater than 10 rule. This is also true for p hat. So p hat is going to be sufficiently normally distributed if n times p times 1 minus p is greater than 10. So this is just a different way of rearranging the slide, but giving you the same information. If you have a random sample of size n with population proportion p, such that n times p times 1 minus p is greater than 10, that means that your random variable x is normally distributed. And the mean of that normal distribution will be n times p, and the standard deviation of that normal distribution will be square root n times p times 1 minus p. But then, if x is normally distributed, that means that p hat must be normally distributed, because p hat is just x divided by some constant number n. And what I want you to notice about the formula for the mean and the standard deviation here is that this mean, so the Greek letter lowercase mu means mean, right? This mean, population mean, of p hat is just going to be equal to the population mean of your x random variable divided by n, because that is what p hat is it's x divided by n. So then this formula for mu sub x was n times p, and whenever I divide by n, the n's cancel, and this is p. So that's how I arrived here at this formula. Remembering that p hat is my sample proportion. Okay, then what about this sigma subscript p hat? Well, that's the standard deviation of the sample proportion. And just like before, this is going to be equal to the standard deviation of your random variable x, your binomially distributed random variable x, divided by n, because again, p hat, the very definition of it is just x divided by n. Now, the formula for this before was square root n times p times 1 minus p, and I could write that as square root n times square root p times 1 minus p. So you might remember that from your last algebra class, that if you're multiplying multiple factors inside a square root, You can just separate the square root anywhere as long as you're still multiplying those together. And then we're going to divide by n, right? So square root n divided by n is going to be a square root n in the denominator, because n itself you can think of as square root n times square root n, and then the square root and that square root will cancel, and that's going to leave us with this, square root p times 1 minus p divided by square root n. But then again, what you may remember from algebra is if you're dividing two square roots, you can actually just host them all underneath the same radical. So this is how we ended up with the formula for this standard deviation of the sample proportion, being square root of p times 1 minus p now divided by n. And of course you take the square root of everything after you've already divided, right? So be careful about the order you put that in your calculator. But these are important formulas for you to know, and I believe that they are still on your formula chart for the exam. So you don't necessarily need to memorize these, but you will need to know these as you're doing your homework. And let's just see, let's go back to our previous example that I used and worked in Microsoft Excel and see if those formulas actually hold. Let's see if, the mean of all of my sample proportions is equal to the population proportion. Well, it was pretty close. My sample mean of all my sample proportions was 0.399, and the population proportion is 2/5, or I should say 2,000 divided by 5,000, which is 0.4. That's very, very close, obviously. The standard deviation, my population standard deviation here, should be the square root of p, which is the population proportion, 0.4, times 1 minus p, which will be 1 minus 0.4, then divided by n, which is my sample size, which is 30, and that is 0.089, which is the same thing as I calculated whenever I took the standard deviation of all of these sample proportions. So I still got 0.089, 0.089, that checks out as well. Of course, these statistics that I calculated, the sample mean and sample standard deviation of this set of sample proportions, they aren't exactly the population proportion and the population standard deviation. They vary by a little bit, but that's to be expected, right? That's the whole idea of a statistic. A statistic is just an estimate of a parameter. Given a certain sample, we're doing the best guess we can to estimate these parameters. But it's never going to be exact. But very, very, very close in this case. Anyways. Okay, so again, what's important for you to remember is that the population mean of your sample proportion, so mu subscript p hat, is just equal to the population proportion, p. And that the standard deviation of the distribution of sample proportions, sigma subscript p hat, is equal to the square root of p times 1 minus p divided by n, where n is your sample size. So let's ask the question, what would be the effect of the sample size what is the effect of sample size on the standard deviation? Well, as your sample size grows, so you increase your sample size from like 30 to 300, that increases the denominator of your standard deviation. But you know that an increase in the denominator means a decrease in the value of the overall fraction, right? So 5 is greater than 4, but 1/5 is smaller than 1/4. And so a larger sample size is going to be a smaller value inside the square root. But the square root function, that's going to give you a smaller value for smaller inputs, right? So square root of 9 is less than square root of 16 because 9 is less than 16. And in any case, the standard deviation of the distribution of the sample proportion is going to be smaller when you have a larger sample size. So let me repeat that. A larger sample size gives you a distribution for the sample proportion that is less dispersed. It's more concentrated around the population proportion. So if we randomly sample 50 students in the example given, what would be the distribution of the sample proportion? Well, to figure out if it's truly normally distributed or not, we have to do n times p times 1 minus p, which is the variance of the binomial distribution. And for us, n is going to be 50 in this case. P is going to be 2/5 because that's the population proportion. And then 1 minus p would be 3/5 because 1 minus 2/5 is 5/5 minus 2/5, so that's 3/5. So I have 50 divided by 5 divided by 5. So that's going to be 2 times 2 times 3, which is 12. And 12 is greater than 10, and so that means that this has to be normally distributed. So the distribution of the sample proportion will be a normal distribution. The mean of the sample proportion is going to be the same as the population proportion, which is going to be 2/5. And the standard deviation of the population proportion is going to be the square root of p times 1 minus p divided by n. So this is square root of 2/5 times 3/5, all then divided by 50. And I'll get out my calculator to do this, but 2/5 times 3/5 is going to be 6/25. And 6/25 divided by 50. Let me just do the math here. 6 out of 25 divided by 50 gives me a very small number. And then when I take the square root of this, I get 0.0693. .0693. And for this mean, 2/5 is 0.4 if you want to represent it like this. Okay, so when I ask you what is the distribution of the sample proportion, you first have to respond what type of distribution is it? Well, it's a normal distribution. And then, by the way, we figured that out because this n times p times 1 minus p was greater than 10, so that means it is normal. Then you have, for the normal distribution, you have to tell me the mean, which we found out is 0.4 using our formulas, and the standard deviation, which we found out is 0.0693 using our formulas. So knowing those three pieces of information, what type of distribution is it, what is the mean, and what is the standard deviation, that's the complete answer to the first bullet point. Now below this, we have, what if we were to randomly sample 100 students? Well, I know that it's still going to be normal, because if 50 times p times 1 minus p was greater than 10, then 100 times p times 1 minus p, well, that's going to be twice as much. And so this is definitely going to be normal. What about my mean? Well, that's still equal to the population proportion, so it is still 0.4. Now, the standard deviation might change. So let's look at this formula again. It's p times 1 minus p divided by n, and then you take the square root of that fraction. So it'd be 2/5 times 3/5, this time divided by 100. 2/5 times 3/5 is 6 divided by 25. This time I'm going to divide by my sample size of 100, and then take the square root of that. And so now my standard deviation is 0.049. So notice that when my sample size increased from 50 to 100, my standard deviation decreased. But of course the mean stayed the same, and it's still normally distributed. In fact, it only becomes more normally distributed when your sample size increases. Here's another example problem, just in case you need to see one more time. This says 16.5% of the residents in the United States are older than 65. So we might say that the population proportion would be like the proportion 0.165, 16.5%. If we were to randomly sample 40 residents, so I say n is equal to 40, what would be the distribution of the sample proportion? Well, is it normal or not? We have to calculate n times p times 1 minus p and figure out if that's greater than 10. So my n times p times 1 minus p is going to be 40 times 0.165 times 1 minus 0.165. N times p times 1 minus p, and that is the number 5.5. So in this case, the distribution is not normal. We can still tell you, though, that this, we can still tell you the mean and the standard deviation. So the mean of this sample proportion is still going to be the population proportion, and the standard deviation of the population proportion is going to be still square root of p times 1 minus p over n. So I want square root of p times 1 minus p divided by n, which is, in our case, I believe 40 residents. Yeah. So the standard deviation is going to be 0.0587. And while that sample proportion still follows a scrunched up binomial distribution, where you take the x-axis and you scale it down by a factor of 1 over n, and so the x-axis is completely contained within 0 to 1 because your proportion has to be between 0 and 1. It's not close enough to a normal distribution, so we won't be able to use the normal distribution to analyze that data. What if we boost this to 400 residents, right? So now my n is no longer 40, but my n is 400. I should calculate n times p times 1 minus p to be 55. And that is actually greater than 10 this time. This time your n times p times 1 minus p is greater than 10, which tells me that this is very nearly normally distributed. And so this is a normal distribution. The mean of this population, sorry, the mean of the sample proportion is still going to be the population proportion. And then the standard deviation of our distribution of sample proportions is still going to be square root of p times 1 minus p divided by n. So square root of p times 1 minus p divided by n. But this time, instead of n being 40, my sample size is 400. And that will change my answer, so I get a smaller standard deviation when my sample size increases, and it's 0.0186. 0.0186. Nice. Okay. Here's one more example problem. I'll go ahead and let you try this one on your own if you like. But we're very nearly getting to 30 minutes. And so the last thing I'll leave you with on this video is to say that for the distribution of the sample proportion, we say that it is normally distributed if n times p times 1 minus p is greater than 10. That's the criterion for p hat being normally distributed. In the previous video, in 8.1, you may have to go back and revisit it, but for the distribution of the sample mean, remember the distribution of the sample mean that distribution was normally distributed if your sample size was greater than 30. So it had a little bit of a simpler criterion for normally assessing normality, just because you didn't have to do any calculation. But be aware of that difference. And if you need to, go back and reference section 8.1. All right, good luck. Have a great week.